This is the first lesson of the new unit. This unit is called quadratic functions. The last unit, Unit 3, was called quadratic algebra. So in the last unit, we looked at more of the equation of the quadratic, and we started manipulating it by expanding or factoring, just putting it into different forms. Now what we're going to do in this unit, quadratic function, is actually look at what visually a quadratic is and its characteristics and so on. So the starting off lesson is lesson 4.1. Can you tell the difference between a linear function, so like a straight line, versus a quadratic, which kind of looks like a U, or neither? So neither could be many things, like a cubic function, a quartic function, an exponential function, a trigonometric function, all of these different types of functions. That's actually something they teach in grade 11, so next year. So right now in grade 10, all we need to do is distinguish between a linear, a quadratic, or everything else. Okay, and there's three ways that we can distinguish between these three options. Number one, we can take a look at the equation, which means just based on what you see as the equation, you can tell which one of those it belongs to, linear, quadratic, or neither. Sorry. The second way is to graph. So based on the graph, you can obviously tell what graph or what function you have. And then lastly is based on the table of values. I'm going to perform something called finite differences. Okay, so let's go back up to number one and we'll just take a look at the equations first. Okay, so we take a look at the degree of the terms of the equation. So normally a quadratic or a linear would be some sort of a polynomial. In which case you'll look at the highest exponent, which is what they mean by degree, and you'll be able to distinguish if it's linear or quadratic. And so if it's a linear, it normally looks like this, which is slope-intercept form, or it looks like this, which is called standard form. And notice that in both cases, your x's and your y's have a degree of 1. Okay, so I know you can't see it because we usually don't write it, it's invisible, but this y has an exponent 1, we don't write it, and this x has an exponent 1. So if they both have exponent 1s, if you decided to, say, graph this or put it into Desmos, it would draw a straight line, which is what we call a linear. Same with this one. This x has a degree of 1, this y has a degree of 1, and therefore this would also be a linear, it would draw a straight line. Now in terms of a quadratic, there are three different forms. You haven't learned this yet. I mean, you've kind of learned this one. This one kind of looks like the simple trinomial or the complex trinomial. This is called standard form for a quadratic. This one you'll learn later is called a vertex form. And then this one is called factored or intercept form. Okay, so this don't worry about just yet. You'll know it's a quadratic because it has a degree 2, which means that the x variable has to have a degree of 2, so an exponent 2, but the y variable has an exponent 1. So if you take a look at this one, the highest x value is this guy, like the highest exponent, and that exponent is a degree 2. We don't really care about this one because it's a smaller degree. We always look at the highest degree, and this one has a degree of 2. So and the y has a degree of 1. So this is a quadratic function. Notice again in this one, we have an exponent 1 for the y, and do you see how this x minus h has a little 2 right here? That means that there's 2 of these x minus h's, and if I actually use like distributive property, I would get an x squared, which automatically makes it a quadratic function because it has a degree 2, x squared. And even this one, if I decided to open this up by doing this expanding, I am going to get an x squared, which again is characteristic of a quadratic. Okay, so let's take a look at some examples and see if we can tell. So state the degree of each of the following equations, then determine if the relations are linear, which I sort of kind of put in pink, blue for quadratic, or neither. Okay, so taking a look at the first one. This one right here has an exponent 2 on the x value. It is a degree 2, which means it's a quadratic. Okay. This one also right here, if you start to expand this and put it so that there's no more brackets, like you expanded and simplified, you're going to get an x squared, which would be, again, a degree 2, and that would be a quadratic. Do you see how this one looks like standard form right here? And this one looks like that factored intercept form. Okay, so those are both quadratics. This one right here looks like the vertex form of the quadratic right here. Okay, in other words, you see that little exponent 2, that means it's a degree 2 and therefore is going to be a quadratic. Now you might say that the very last one also has exponents of 2's, and so how come I didn't highlight that one blue? Well, we had said that only the x value should have an exponent 2, but the y value has to have an exponent 1. So see how there's like a 2 right there? The y is squared. I don't know if you recognize this, but this is a circle, right? So that's not going to be a quadratic. That is a neither. It's a completely different function. It graphs a circle. It doesn't graph a quadratic. Okay. This one is actually a little bit different. It doesn't have the exponent 2, the variable is in here. This, if you were to graph it on Desmos, which you totally can, and see what it looks like, sorry, it's an exponential graph. And so it's neither linear, it's not quadratic, it's a different class on its own. Okay. This guy is in standard form. All of the x and y variables have exponent 1's, and so it's a degree 1. I guess that pink didn't show up very well when I scanned it, but it is this guy right here. So it's a linear. Okay, and that's how you can categorize them as linear, quadratic, or neither just based on the equation. Now, based on the graph is obviously much easier because you can visualize it. If it's a straight line, it's a linear. If it's a U-shaped, either happy face or frowny face, it is a quadratic. Okay, now I must preface that this linear has to be straight, like from one end to the other end continuously. Okay, and so if we give you several different examples, determine whether each of the following is linear, quadratic, or neither. Oh, I did this wrong actually. Oh, okay. And this is where learning comes and I make mistakes too. Actually, none of these are linear or quadratic. I apologize. That should have been yellow. My mistake. Let me go through them. This is an exponential graph. It is neither straight, it's not a U, and so this is categorized as a neither. I got this right. This one does look like two straight lines. This is actually an absolute value graph. You'll learn it next year, I think. And it does look like a straight line, but it's not continuous from one side all the way to the other. There's like a bend in it, right? So it comes to like a peak. That is not considered a linear graph. It is considered an absolute value graph if you want to look it up. Okay, so this is a neither. Now this, I apologize, I looked at it and just immediately saw the curve and decided to put it blue. It's not actually. This guy is called, I believe from my very long ago high school years, a hyperbola, I believe, or it's possibly a quadratic but rotated around, which wouldn't make it a quadratic anymore. And so I apologize, this should be a neither. Okay, yellow. I went too fast, I highlighted too fast. A quadratic has to look like either a frowning face or a happy face. It can't look like a sideways. All right, so that's something different. Okay, then we get into the finite differences. And I think this is easiest to explain. You can read through all the instructions, but it's actually easiest to explain when I show you. And so what they'll do is they'll give you a table. Okay, this is all of my work, so they'll just give you a table like this, table of values. And it says use finite differences to determine whether each function is linear, quadratic, or neither. And so if you look at the numbers, you can't really tell. And you'd be like, well, that's easy. I'll just graph these. No, you're not allowed to graph them, or else you would be using graphs. So this is just based on the table. What you do is you calculate the first differences, and if you have to, the second differences. So I'm going to show you this one first. What you do is you calculate the first, sorry, that's a 1 st, so a first differences, so first diff. The way that you do that is you only focus on the y values. Although I should preface, make sure that all of your x values are going up by the same amount each time. So it does look like they're going up by ones. So that's number one, check mark. Then number two, you're going to take your y values and you're going to subtract them. That's why they call them differences. Okay, now here's the catch. Make sure you subtract in the right way. You always take the bottom one and then you subtract the one on the top. So notice that I put this like little pointer. I'm going to take these two and subtract them, but you're going to take -7 first and then subtract the -9. So be careful with the subtract -9. This is going to become a plus, right? So -7 plus 9 gives me a 2. And then you do it for all the y values, so all the pairs. So I'm going to point to these two now, all right? And I'm going to take the -5, so the bottom one, subtract the top one, -5 minus -7. And that's going to be a 2 as well because those two negatives make a positive. And you keep doing that. -3 minus -5, which gave me a 2. -1 minus -3, which gave me a 2. If all of these numbers, the differences for the first difference column are the same, it automatically means this is a linear. If I decided to plot all these coordinates, it would make a straight line. Now, if I decided to calculate all the first differences, again, noting that all the x values are going up by the same amount, and taking all the y values and subtracting them, bottom, see -2, subtract the top, which is a 1, that will make -3. And if I do that for all of these pairs of y values, I notice they're not the same. Therefore, this is not a linear function. So I'll continue and I'll subtract all the first differences in the same manner. Take the bottom number, subtract the top number. So 1 minus -3. This is going to be a positive 4. 5 minus the 1. That's going to be a 4. 9 minus the 5. That's going to be a 4. If all of your second differences, so see how this is like the second difference column, if they're all the same, then that means you have a quadratic. And then you stop. So like notice that I've already distinguished this one as a linear. Don't keep going to the second differences. You already like identified it as a linear, right? Only when they're not the same do you want to go one step further and find those differences and say, okay, it's a quadratic. Okay, now what happens if you do the first differences? Notice I didn't show my work this time. I just showed the answers of the subtraction. You can totally do that and save some time. Okay, notice that I showed all my answers for the first and second differences and none of them are the same. None of them are the same, which means that it's neither. Like it's not linear because none of these are the same. It's not quadratic because none of these are the same. So it must be something else. And again, if you want to see in Desmos, you can just graph these pairs of coordinates and you can take a look at what it looks like. Okay, so those are the 3 different methods of determining whether your random function is going to be a linear, quadratic, or neither.